Deputy Research Director for HILT CRC. I'm also the research lead for our cross-cutting technologies program, which covers a whole range of technologies, including process heat and thermal energy storage and alternative fuels and all sorts of good stuff. I'm going to be hosting our webinar today. It's being brought to us by Keith Lovegrove. Keith will be known to many of you, and I'll do a bit of an intro to Keith in a moment. He's going to be talking about some work that he's been doing recently on process heat. And then we've also asked one of our lead researchers in HILT, John Pye from ANU, to give us a bit of a HILT perspective. So for those that are either working with HILT or know of HILT, John will talk a little bit about why the work that Keith's done is so important for us and how it's sort of relevant for the work that we're doing in HILT. So that's enough of sort of context. I wanted to get control of my screen. I wanted to give an acknowledgement of country. I'm coming to you from Ghana land on the Adelaide Plains, and I want to acknowledge the traditional owners of the land and offer my respect for their spiritual relationship with their country, acknowledge that the Ghana people as the custodians of the Adelaide region and that their cultural and heritage beliefs are still as important to living Ghana people today. Very simple agenda today. Once I've finished doing the introduction, we'll hear from Keith. We've asked Keith to speak for 25-30 minutes. And then, as I mentioned, John will give a perspective from HILT, and he'll talk a little bit about one of his HILT CRC projects, but it's particularly relevant in this area as part of that context. And then we should have plenty of time for Q&A. A little bit more detail on Keith and John. I won't go through each of these in detail, but as you can see, Keith's his background at ANU, worked there as a researcher on solar thermal, since moved away from the university, has been working in industry for some while now, but maintaining links with industry, with research through his various other activities with ARENA and University of Adelaide Centre for Energy Technology. There's John's brief bio. Researcher at ANU and doing lots of good work for HILT. As I said, he'll talk a little bit about that. So that's probably more than enough from me. I'm going to hand over to Keith at that point. I'm going to stop sharing my screen and hand over to you, Keith.
Thanks, Peter, and good afternoon, everybody. Just let me bring some slides up. And from the beginning. Okay, is that visible, Peter?
Yes, all clear, Keith.
All clear. Okay, so what I'd like to introduce you to this afternoon is the Australian industrial process heat market, and the report title is Towards Zero Emissions. Some of the people online may know that we produced the report back in 2019, Renewable Energy Options for Industrial Process Heat, which was commissioned by ARENA. And we had some technical partners working with us on that. What this report, this April 2025 report, is essentially an update. It's a sort of shorter update. In fact, we would recommend that people read both reports together. The 2019 version is a much longer, in-depth technical analysis of technical options and explains the methodology for the analysis in more detail than the 2025 version does. There's a link there and we'll share these slides later, so you can get both reports from that link. So, industrial heat use in context. If we look at total final energy consumption in Australia, what we see is 47% industry, and the definition of industry, I guess, here is anything commercial except building. So other commercial is kind of building, space heating and cooling and so on. And then, of course, there's transport there and residential. So 47% industry. And what does industry do? Well, fuels for heat is 42% of the 47%. So roughly 20% of Australia's total final energy consumption is industrial heat. How are we getting that at the moment? Well, just over half of it is from natural gas. Black coal is still quite a bit, but there is already quite a lot of renewables, 10% in the form of sugarcane waste and wood waste and so on. Figures a little bit, and there's a tiny little bit there of electricity already used for heat. Okay, that's what we're using. When we say fuels for heat, 842 petajoules, roughly speaking, if we take a kind of average 80% process efficiency, it means the end use is 674 petajoules of heat used at various temperatures. And this is important because, as we'll see in a minute, different temperatures give you different options for your renewable energy. So there's 10% that's less than 150 degrees, 150 to 250, 41%. And so, for example, the 9% that's less than 150 is sort of the absolutely stretching the limit of what you might be able to reach with a heat pump, for example. But when you go into the 150 to 250, you've got to look at other options. Okay, who's using this energy? Different sectors, and there's some real biggies. And the biggest is alumina refineries, and that's grouped together with other non-ferrous mineral processing. Oil and gas is a biggie. Food and beverage is a biggie. Then iron, steel, petroleum refining, ammonia, and so on down the list. But it's worth noting that food and beverage, sitting there at number 3, is the one that's using all the sugarcane waste. So it's actually distorted a little bit by counting all the sugar refineries in it and the fact that they're already using a lot of renewables. So if you would cut that off, food and beverage would drop right back down the list quite a bit. Splitting it by temperature, as you can see in the table up there, and looking at the different sectors and what fuels they're using and so on, and trying to estimate what they're paying for fuels at the moment, the total market there is $10 billion a year, roughly speaking, being spent on fuels for process heat for industry. So it's a fair bit of cash moving around in that sector. Where is it happening? This is important. Location. If you're thinking of a solar-driven thing, then location's pretty critical. If it's a straight electrification or hydrogen substitution, then I guess location doesn't matter. Location's also going to be relevant if you're targeting a biomass solution. So it's actually hard to work out how many sites there are and what the definition is. We said greater than 15,000, is it 20,000, 25,000? It also depends on the definition. What we do have is it's almost an exponentially decaying sort of distribution. We have many, many sites using a little bit of energy, tailing off to just a few sites using a hell of a lot of energy. So greater than 1,500 sites using 10 terajoules per year. The map there, as well as picking out the sectors by colour, we've got a sort of size of the spots, which is a sort of logarithmic scale, because that's the only way you can grasp the whole picture, is to sort of think of these things on logarithmic scales. To try and, I personally relate much more to trying to think of an average usage in megawatts thermal. So those big ones at 40,000, they're like a gigawatt of continuous heat use, whereas right down to the 10 terajoules, that's like hundreds of kilowatts of scale of heat use. That map, even with our attempt at logarithmic scales, there's many sites that the dots are too small to actually show on the map, and a lot of those are clustered around the capital cities, as you'd expect. You can see the biggies there. The maroon colour, which is the alumina refineries in Queensland and Western Australia, although Mount Isa copper is also in that category. the two steel making sites, Port Kembla and of course Whyalla, are shown there, and you can see the sugar refineries, the orange ones right up there in Queensland, sort of in the mid-range of size. Okay, so some observations on the key sectors, starting with alumina. What have we got here? It's just 6 large alumina refineries plus the copper, and you've got this interesting situation where the heat use is split between digestion processes at sort of less than 200 degrees C and calcining processes that traditionally have been over 1,000 degrees C, but let's say over 800. The size and the scale doesn't really speak to bioenergy solutions. There are multiple options for the low temperature, and certainly CSP, solar thermal, although we know that renewable electric-driven mechanical vapor recompression is already being applied. With the high temperature things, well, one could think about swapping in hydrogen for natural gas. And of course, HILT's working in this area, and steam calcination is a very promising thing as well, I know. With these big sectors like alumina refineries, as a nation, it would be nice to think about, as we grow our economy and try to become more sustainable, actually thinking about greenfield siting, where obviously you need to be sited relative to the resource you're processing, but also thinking about the renewable resource, or particularly the solar resource, would be worthwhile. Okay, down to food and beverage. As I've said, the sugar mills using the bagasse, the sugarcane waste, are actually dominating the picture, but it's a very good precedent for a renewable solution. Many applications are economic. There's quite a lot of low temperature hot water steam use, lots of options for that. Any food production that has its own waste, there's usually a waste disposal problem, you could say. So using your own biomass kills 2 birds with 1 stone, and is very prospective. But nonetheless, all the technologies should be considered in that sector. Ammonia is an interesting one. Again, 7 large ammonia plants dominating the whole sector. We use it for fertilizer and explosives. And what we're doing is this pie chart here is just talking about the heat use, but there's, in terms of the natural gas there that's going into heat, there's twice as much again, which is actually the feedstock. So the heat is burning natural gas to do steam reforming of methane to get hydrogen, from which you then make ammonia. So that's interesting in many ways. CSIRO have done a lot of work previously on solar thermal driven steam reforming of methane, and it's not getting a lot of attention at the moment, but it's certainly worth keeping in mind. I find this very interesting because it's a case that you could use renewable hydrogen and produce green ammonia, and sure, you've got to think about, well, what's the price of what cost can I make hydrogen for to make a go of this? But if you did this in a greenfields way, you can avoid the capital cost of all of the steam reforming of methane plants. So it's a sort of plausible link to our future export agendas and so on. Iron and steel, well, here's where we're using a lot of black coal, and I'm sure John will have quite a lot more to say about this. You can think about some substitution in existing blast furnaces. You could imagine doing it with biochar, but where on earth would you get that much biomass? You can inject some hydrogen, but direct reduced iron is an established technology using natural gas. Anyway, John will tell us more about this, I'm sure. Cement and lime, an interesting one. Again, a few large sites dominate, very high temperatures, but on the other hand, they've already got a track record of burning commercial and industrial waste in the kilns. But the big elephant in the room for that sector is that CO2 is inherently produced by reducing limestone. So we're going to have to do something. We're going to have to either move to a different cement, or else this will be a case where you have to capture CO2 and sequester it, or we don't really have a future in that industry. Pulp and paper, 5 large mills, lots of biomass use. But there is scope actually to increase the other thermal renewables and think about redirecting the biomass to higher values, maybe liquid fuels and sustainable aviation fuels, or who knows what. Oil and gas, it shows as a big heat user, but if this is all about tracking a path to net zero, then you have to ask the question, well, what is the future for that sector? And that's a whole debate of its own. Okay, renewable technologies. Periodically, we hear people pop up with the slogan, electrify everything, and frankly, I get slightly irritated by that because it's a very simplistic slogan, and it just misses the complexity of the energy system and the complexity of these sectors, and the fact there's multiple technology choices to look at. Bioenergy is the dominant renewable source of heat in the industrial sector right now, and it's continuing to get deployed, so not to be forgotten. You can, if you've got wet biomass, digesters to biomethane, burning that. If you've got dry biomass, combustion boilers, and so on. Geothermal gets completely forgotten about. We've got the whole Great Artesian Basin and a bunch of other aquifers around the place where water is there, just water, at elevated temperatures, up to 95 degrees C, sometimes lower. You have to be a big enough energy user to justify drilling the borehole. So there's a very big fixed cost there. You obviously have to be sitting on an aquifer, so that's only, I would say, a large minority of energy users might find themselves sitting on an aquifer. But if you tick those boxes and you have a need for hot water, then this is really cost-effective stuff that shouldn't be forgotten. And of course, electricity is very important, and that can come in a number of forms. If we do resistive heating, there's ETES. ETES stands for electric thermal energy storage. So you can, with a resistive heating, you're committing some sort of thermodynamic crime, turning electricity into heat like that, but at least you can do it at very high temperatures, and so that actually helps with the storage. Heat pumps, on the other hand, use electricity in a thermodynamically appropriate way, with a proper coefficient of performance greater than 1. But as I mentioned before, they'd probably maxing out at 150 or less than 150. There's a picture there of a mechanical vapor recompression unit, and I suppose that is a version of a heat pump that if you start, it's a temperature lift that's hard. So if you start with something that's already hot and you lift it to a slightly higher temperature, that's doable as well. There's other things too, like inductive heating, which are more about process redesign than actually just simply providing one-for-one replacement. Hydrogen, of course, can more or less swap in wherever natural gas is at the moment. Obviously, the combustors will have to be slightly different, but not hugely. So the issue there is, well, can you make hydrogen at something close to a competitive price to the natural gas you're currently using? And finally, solar thermal, which I've got a long personal interest in, certainly has a role to play. So some quick case studies to remind people that this is pretty real, recent ones. So this is a really nice example at Mars Pet Care, and I've got 2 examples from Mars. They've really showing the way as a large global corporation, really embracing the journey to net zero, and what they've already got working in Wodonga as of 2023 is that big orange box there, which is a graphite energy unit. It's electric heaters in blocks of graphite, and I believe the temperature it gets up to is about 700 degrees. So the graphite is storing the heat, and there's boiler tubes wound through those blocks so that steam can be produced on demand. And the nice thing about an ETES with thermal storage like that, okay, it's electric to heat, but with the storage, you can target cheaper wholesale electricity costs on the spot market. So that is the way to make that sort of approach competitive. Heat pumps have been around for a long time, but a recent installation here, this is called a high lift heat pump in as much as it's going from ambient temperature to 75 degrees, so still a long way off the higher temperatures. It's just a big compressor basically. There is a person standing behind that thing just to give you a sense of scale. So a decent unit at a meatworks, 1 megawatt thermal in that case. The solar thermal example, this picture here is from Seville in Spain, a 30 megawatt solar thermal trough. We've tried to use Australian examples where we can, but this is relevant because Mars, the same site where they've put in the graphite energy system, they've committed to, or indeed started site works on an 18 megawatt solar thermal array using these trough concentrators that you can see there. So that'll be quite a boost to the solar thermal sector when it's done. And to finish off, a biomass example, there's many boilers like this around the country. Certainly sawmills where you've got the biomass waste of your own. This works extremely well, replacing natural gas that was previously used, 174 degrees hot water in that case. Okie doke. All right, let's move on to thinking about the economics a bit. And this is a fairly busy slide, which I'll talk you all through. First of all, we've got on the x-axis there annual heat consumption in terajoules per year. And it's a logarithmic scale, starting at 1, going over to 10,000 or so there. And the table there just sort of tries to put that in context. So 10,000 terajoules per year would be a 400 megawatt thermal operation running at an 80% average usage, something like that, which would be sort of getting into the territory of alumina refineries. Probably some of them are twice as big as that. 1,000 terajoules, 40 megawatts thermal, kind of like a paper and pulp unit. 100 terajoules, 4 megawatts thermal, medium sort of food, dairy. 10 terajoules per year is in the hundreds of kilowatts. Modest size factory, 1 terajoule for tens of kilowatts. It's a small business. And below that, you could even, think about mums and dads, bakeries and things using just in the even less than that maybe. So, okay, that's what the x-axis is all about. On the left axis there, we've got levelized cost of heat, or cost of heat, shall we say. So what are all these lines and coloured regions supposed to indicate? If you look, firstly, let's just look at the orange band in the middle there. Go to the far right, the very largest users are basically buying gas at the wholesale price out of transmission pipelines, and they're using gas at a certain efficiency. So if the wholesale price is somewhere between $12 and $15 a gigajoule, then the cost of the heat from burning that gas will be $15 or more a gigajoule, depending on what efficiency it's done at. So that's the biggest users. On the other hand, if you go right to the far left, the smallest users, they'll actually be paying, on top of the wholesale price, they've got to pay for all of the distribution costs and the retailing and so on. And very small users will be seeing prices for their gas, which are pretty much what we see in the home. So suddenly it's the heat cost is now up in the $35 to $45 a gigajoule, and it's got that sort of curve. It's a very rule of thumb curve that we're proposing as the range of likely gas costs. Then at the small scale above that, we've got more expensive heat provided by LPG, which is those regional users who don't have a gas connection are forced to pay a bit more, even again, to use LPG rather than natural gas. at the far right, the bigger end of town can access coal for process heat, and that'll on the whole be cheaper than natural gas. So that's the sort of grey region there. So the two black dotted lines for the bounds of natural gas. I'm now going to carry that over to some graphs that look at the levelized cost of heat from other sources. So let's start with bioenergy. You say, oh, well, if I'm going to use bioenergy, it's really about the cost of the biomass that I buy, and that can range from 0 for waste of my own up to maybe $15 a gigajoule if you're buying in sort of crop material that has to be brought in by truck. So the grey hashed region overlaying all of that is the range of likely gas heat costs from the other graph laid on top of it. So basically, if we can find a renewable solution that falls within the hashed band or below it, then it's worth seriously looking at it with the proper site-based kind of study. So what you see here is, okay, the biomass, look, if we look at the waste biomass at $0 a gigajoule, there's a cost of heat that is not zero and gets bigger as you go smaller. What's that? It's amortizing the capital cost of the boiler that you must buy. And the fact is, the larger the boiler, the more cost effective it is. The smaller the boiler, the less cost effective it is. That's why the levelized cost of heat rises up as you get to small sizes. But what you see is it sort of parallels the higher prices you pay for your gas. So waste biomass is clearly in the money. $5 a gigajoule biomass is probably in the money, and $10 a gigajoule biomass is still worth seriously investigating. The width of the green bands, by the way, is just to convey a sense of the range of uncertainty and different configurations people have. Okay, electrification options. Heat pumps first. What we see here is a similar kind of curve that says, well, you've got to cover the capex, and that'll be less cost effective at small sizes. But in this case, we've fixed the cost of electricity for the sake of this analysis at $100 a megawatt hour. And what happens is the higher the temperature lift, the lower the coefficient of performance. A low temperature lift is going to have, COP of 4 or 5, who knows. So you get a lot more heat for the amount of electricity you put in. That means the levelized cost of that heat is going to be lower. So 30-degree temperature lifts look very economic indeed. 80-degree temperature lifts, definitely worth considering. But at 130, well, you can't buy the units anyway, but it's starting to not really make sense economically at that sort of temperature lift. On the other hand, the ETES is a different story. In this case, it's very much dependent on what is the price of the electricity. The COP, it's 1 for 1. You just put in a gigajoule of electricity, you get a gigajoule of heat, more or less. A bit of inefficiencies there. But with your storage system, you've got a chance to chase lower costs of electricity. And if you can find a sufficiently cheap average price of electricity, which is conceivable, it turns out when you look at the spot price history, Victoria seems to deliver the best chances of finding the average cost of electricity in that low region. But nonetheless, other states too, you can access, say, with 6 hours of storage where you just take the cheapest intervals during the day, it looks like it's got a role to play for sure. Geothermal, I alluded to that before. It's got a very high fixed cost to making these boreholes. So you have to be above 20 or 30 terajoules per year to even bother. And you have to be sitting on an aquifer with hot water. And your heat use has to be below 100 degrees C. But if all those things, if you can tick all those boxes, what you can see is above 40 terajoules per year, it looks like really cheap heat. So should not be neglected by some of our large regional players. Think about regional abattoirs who happen to be in the Great Artesian Basin, it'd probably be really useful for them. And finally, I'll go to solar thermal. And what we've got in this case is a temperature dependence. So solar thermal, you can go from your flat plate, coils on the roof for your swimming pool heating, to solar heat systems for your hot water, through to small concentrators, parabolic troughs to get modest temperatures, and then on to heliostat tower type systems. And what you see is the higher the temperature you want, the greater complexity there is in the technology. And there's almost a sort of rule of thumb linear relationship between the temperature you want and the cost per installed kilowatt of the technology. But then, of course, like all the others, there's this size dependence where the bigger you make it, the more cost effective it is. So we see the curves again. So what we see is 100 degrees C, it looks really cheap relative to gas. Presuming you're in a reasonable sunny place, it'll be worse in southwest Tasmania than it is in northern South Australia, for example. 200 degrees C is definitely worth considering, particularly for bigger systems. 400 degrees C, starting to get marginal. 600, it's struggling a bit. But I should preface all this by saying this is just straight out economic comparisons and doesn't speak to the fact that we've committed as a nation to net zero by 2050, and we need to be considering an implicit carbon price in here. And that certainly, I mean, in a sense, we must decarbonise all these sectors. We just want to do it as cheaply as possible. And it's good to know the relativity of the different solutions. So wrapping it up now, industrial heat use is around 20% of Australia's energy end use. It's a small number of very large sites plus many smaller ones. It's currently about gas and coal. There's a lot of heat use below 250, easier to replace. There's a lot of heat use above 600 degrees, challenging. Good job for the HILT CRC. Renewable energy options are there for all current industrial uses. If we look at short to medium term opportunities, that might be 220 odd petajoules. We could save $4 billion a year in actual fossil fuel costs. And the challenges we face is that the experience with renewable heat in industry is low, and the barriers include a very low appetite for risk and short payback time expectations. So these are the realities we have to take into it. So thanks, everyone. Thanks, Peter. I'll stop sharing.
Great. Thanks, Keith. Perfectly at the time. Well done. So as I mentioned, we're going to get a brief presentation from John Pye.
So I should plunge in and give you my comments and HILT perspectives.
Right.
Thanks for the great presentation, Keith. I read the updated report very closely, and I think it's a great piece of work. And for those that aren't aware, Keith Lovegrove is probably the reason I've been living in Canberra for the last 15 years. I joined Keith's group when he was at ANU, and we worked together for quite a few years. So I've got a couple of perspectives from our green heat project and also from our variability and loss production project, and as time permits, I've got a few other little comments. The first thing, jumping into the project RP2003 Green Heat for Industry that we did here in the HILT CRC early on. This was an attempt similar and in fact inspired by the earlier version of Keith's report, I would say, to come up with some costs for different renewable heat options. We thought about concentrating solar into thermal storage. We talked about, we considered photovoltaics, wind, and a combination of photovoltaics and wind into either thermal storage with a heater or into electrical storage and then a heater to a load. And we also considered the different renewable electricity options into an electrolyzer, into hydrogen storage, and into a hydrogen burner. And we didn't treat biomass terribly seriously because of concerns about the scale when you apply it to heavy industry. And in our study, we were very interested in capacity factor. So how much do we oversize the energy input? How big does the storage need to be in order to achieve different levels of reliability in meeting what in industry is typically a constant load, but we assess the cost of meeting different fractions of a constant load. So we had linear models. This big diagram here is showing the PV wind hybrid case going into thermal energy storage. We had electric storage, we had the CST case, we had the hydrogen case, which is also coming from a project that Joe Coventry led early in the CRC, looking at the cost of firmed hydrogen. I won't go through all of our assumptions, but we tried to take sort of safe assumptions for costs of things, and we considered five different locations around Australia, spanning from Burnie, which has got fantastic wind and not very good solar, to the Pilbara with great solar and not very good wind, and sort of a few in betweens aligned with where industry is in Australia. Just to quickly cover key things that we saw. In the Pilbara, for example, it was clear that concentrating solar with our cost assumptions came out as a very competitive option, especially at lower capacity factors. But as you went to higher capacity factors, all of these curves bent upwards, and in particular, CST bent upwards to the point where at something approaching 100% capacity factor, the hybrid PV wind system, even in the Pilbara, kind of gets to about parity, which we thought was really interesting. And that hybrid of PV wind and thermal storage was kind of the winner across the board for applications needing heat. So if you need heat, store heat was a key observation from our work. But then the other thing that's jumping out is that firmed hydrogen, especially if you've got access to low-cost salt cavern storage, is surprisingly close. And in our future projections, which I've skipped over, in our future projections in places like Burnie, it seems that hydrogen might even be a cheaper form of heat than thermal storage, which is really interesting. So systems that store electricity generally not as competitive as systems that store heat. There was a lot of emphasis, because our focus is on heavy industry, we talked a lot about whether high temperature would be a problem, especially for concentrating solar power. And yes, it would. The higher the temperature you go to, the more you've got all these losses that start to mount up, especially radiation from the aperture of a concentrating solar collector. And so as Keith's report concludes, it's quite hard to see high temperature CST being competitive in the even the longer term. So a lot of, I think, agreeing on a lot of points in that work there. Our other project that I wanted to mention really quickly is a variability and loss production project, and Peter Ashman is also involved in this project. What we were trying to look at here was balancing all of these variable renewable energy inputs and the cost of firming them up with storage and so on, with a process that's potentially able to be operated in a variable way, flexibly. So, you know, we saw the cost of energy inputs rising for high capacity factor. Well, what if our process can be more flexible and get some balance there? And Keith going to talk a lot about green iron and steel processes here, but I actually chose today to talk about the cement clinker process, which actually was Peter's team's input, and Saw and Shai from University of Adelaide did some nice process modelling. They looked at a generic cement plant where the calciner was replaced by an electric calciner, something like the Lilac process from our colleagues at Calix. And the idea was that the whole process has to ramp up and down in harmony, the rotary kiln and the calciner together. But they looked at the flow sheet very carefully and found that it was possible to ramp down a process like that to maybe 55% of its normal output. So if you have a process where you can do that, and you imagine that it might be a retrofit even, you consider, well, what happens to the levelized cost of our product if we back off from 100% capacity factor to something less than that? So 100% capacity factor means the highest cost of energy, lots and lots of storage that you're paying for. If you back off to 99% or 98%, 95%, or all the way to 80%, it changes the levelized cost of product. And what we found was the cheapest levelized cost of product was at surprisingly high capacity factors, 97%, 95%, even 99%. The top graph here is in a system where we assume only photovoltaics is the input, which and this is for the region around Adelaide. So that's more expensive than a system that combines photovoltaics and wind. So when the energy input is optimized, in other words, cheaper at a given capacity factor, the system balances and you put more money into storage and you run at a higher capacity factor. So the summary of all of this, I suppose, is that we do really need, even in retrofit cases, it was similar for our greenfield iron and steel study. When you look at the cost of lost production, that's a really dominant cost, and it really pushes you to running nearly continuously, and that's because costs of lost production really mount up if you go down to, say, 80% capacity factor, and the savings in storage are not enough. The savings in storage and overbuild. So I got a whole long list of further comments into details of Keith's very nice work, but I think you said, Peter, that you had plenty of questions from the audience, and so maybe up to you. It might be better to go back to everyone who's listening and wants to use the time.
Yep, thanks, John. That's great. So yeah, there is a little bit more in the Q&A and the chat that we could pick up on. Some comments that I might just replay for you, Keith, and John, feel free to jump in as well. So in the Q&A, we've got something here from Vera, which says a significant amount of waste heat is generated in the iron and steel industry, high temperature. However, when we consider heat recovery projects, they often become financially unviable. So I think that's more about waste heat. I'm not sure if you've got any thoughts on that one, Keith, or...
Yes, I suppose what that's really telling us is that from the point of view of the people who created it, the iron and steel, it's waste heat because it's at too low a temperature for them to use. So yeah, you have to find a use for the waste heat is the problem. And there'll be someone somewhere in the country who would love to have that heat, but if they're not co-located, it's not really going to work, is it?
Actually, Keith, that reminds me of something I was going to ask you about. So I mean, looking at all of your cost curves, they all go alarmingly skyward as you get to very small scales. And I'm just wondering whether you've got any thoughts on aggregation, of some of those smaller users. Is there any benefit for them to kind of get together and work on something?
That's a really good point, Peter. Yes, that's right. If you could aggregate small users in a precinct and have, a streamlined network linking them all up, then the cost of the heat would be there'd be one bit of plant with a more cost-effective capex. Yeah, absolutely. Yeah, we could do that.
In some old-fashioned industrial precincts where you've got perhaps large users that have got waste heat at high temperature that they can then cascade down to other users.
Yep. No, that's absolutely right. Yeah. Which sort of speaks to, we tend to come at all of this as a sort of retrofit. Oh, we've got all these factories. How are we going to decarbonise them? Which is obviously the valid short-term thinking. But, if we can be more visionary, we should start factoring in energy to our site choice. Whereas historically, energy's been a really small part of putting together industrial sites and hasn't driven the site choice. But now, I'm not saying that it should dominate the site choice, but it should certainly play a bigger role.
Yeah, and I guess a lot of that's historical from a time when energy was relatively cheap.
Yeah,
I mean, in some industries, the energy price very much dominates location. Think of aluminium smelting, for example. There's a comment
on that site selection question, Peter. I thought it was very interesting the work that the Superpower Institute published recently. They were finding, and this again is consistent with work we've done in HILT CRC, that not so much. It's amazing that the location of the cheapest energy doesn't seem to drive things, but rather the location of the cheapest sort of labour costs. potentially is the driver. And, you know, they ended up finding that the Pilbara was definitely not the best place for a green steel industry, despite much better energy resources, because the costs of those remote sites are so high, and so they become dominant.
Yeah, no, good point, John. Keith, there's another comment in the chat from David Hicks, and I'm hoping you might understand it a little better than I do. He says, just a comment as to the cost of heat from fossil fuels. It would be interesting to see a holistic costing model, not just the wholesale price paid. Not quite sure what he means.
Okay, I think if people can imagine in their heads that first graph where I looked at the cost of heat from fossil fuels, there was an upper line on the gas fuel costs, which included the amortization of the capital cost of a new fossil fuel boiler or whatever. Whereas the bottom line was purely fuel saving. So we've tried actually in that band, that sort of hashed grey band that's on the other LCOH graphs, the upper end of it is supposed to be, I think, the holistic full picture that he's asking for, whereas the lower level is the lower end of fuel savings only, where your gas boiler is already amortized. Hopefully that helps.
Yeah, Keith, he's just
and when we have capital costs in there for things, we've got operation and maintenance factored in as well, for example. Yeah.
David's just added another comment, which I think is suggesting that he means more, you know, not just the cost, but also the life cycle. So, you know, and you alluded to this a little bit in your presentation, how do we actually account for how do we ascribe some value to the decarbonisation process that we're trying to drive, whether that's a cost of carbon or a premium on a green product or whatever that might be?
Yes. I mean, John or Peter, you might have this at the tip of your tongue better than me, but I think roughly speaking, an Australian carbon credit unit at the moment is like $35 a tonne, which is pretty low-ish. That might add $1.50 a gigajoule onto gas costs. Does that make sense to you, Peter?
I think so.
Yeah. So it's not. I mean, if you think that's the cost, then I mean, he's asking very valid questions. Here we are. I've just done this sort of simplistic. Well, is the renewable competitive with the fossil fuel? Yes or no? Which is probably the mindset of a factory owner at present. But we are supposed to decarbonise the whole economy by 2050. So the question is not, is it competitive with natural gas? It's just, what's the cheapest way we can get this job done? And can we get it done for $35 a tonne avoided carbon? Probably not. We'll probably go up higher than that, I think, by the time we get it done. Yeah, once upon a time people talked about emissions trading, but it doesn't get discussed anymore. Strange thing.
Our work on the cost of green steel processes concluded that we needed something like the recent European carbon price of 90 euros or about 150 US a tonne to make our hydrogen ion making process cost competitive. And that was about the same number that the Superpower Institute in their study concluded. But they also made the interesting point that the $2 a kilogram hydrogen incentive that the government's currently put in place in Australia does about 2/3 of that work. I haven't sort of fed that number into our models, but so we don't have a carbon price, but there are lots of other ways that incentives can be put in place, and I think that's very much under consideration by the government at the moment.
Keith, I was going to ask you about, you mentioned that in paper, pulp and paper, there's a lot of bioenergy already being used for obvious reasons. Is that exclusively sawmill waste, or are they now starting to look at forestry wastes as well?
Look, I'm not a super expert on that sector, but I'm pretty sure. Yeah, I guess it's a mixture, although I don't know what the definition is, or, where it's forestry waste and where it's sawmill waste. I mean, sawmill waste, I guess, would be purely sawdust, but I think they are using wood chips from, the trimmings and whatnot. Is certainly part of it. Yeah.
Yeah, that's right. There's the hog fuel, as I think they call it, which is all those trimmings and bits and pieces. I don't know. I think there's a lot of material left on the forest floor too that maybe can be thought about. But the other thing in pulp and paper is the dissolved lignin in the, especially in the craft process. So the what do they call it? The boiler anyway, which is separating out the chemicals. There's a lot of heat comes from that recovery boiler, I think it's called. Yeah. So there's the hog fuel, and then there's the recovery boiler. Two important heat sources in that sector.
One of the things to think about, both in that sector and maybe sugarcane bagasse waste, is that those sectors are already using biomass, because to them it's waste they have to get rid of. So they're using it because it's traditionally cheapest and a problem. So they haven't been really motivated to use it to its best value and highest efficiency. Because if we switch our thinking around and think, well, actually a biomass is a pretty valuable, inherently valuable thing, we should squeeze the most value out of it we can. I mean, here we are talking about heat for industry, but really goes to that holistic point that the viewer raised before. We kind of need to think about all sectors, and it might be that we should prioritise biomass into things like sustainable aviation fuel. So actually take that stuff, gasify it, do Fischer-Tropsch, get really high value fuels out of it, and rather, where we just want process heat, maybe we should put another renewable in there as well. So yeah, definitely want to think the big picture.
Another application for biomass that we talk about a little bit in the HILT CRC is the carbon that you need for carburization of steel. So that could also be a place where biochar or something like that could be fed in. Yeah,
that's an interesting thing too. We did a piece of work a few years ago looking at the chemical feedstocks that the nation needs, and I highlighted ammonia production. Okay, great. Why do we make ammonia? It's for fertilizers and explosives. It turns out that most of the fertilizer use in Australia is in the form of urea. Well, if you want to make a urea molecule, you need a carbon molecule to do it. And so, it's like, oh, wonderful, we can have green ammonia. Sure, we can. But if we want green urea, we're going to need a lot of carbon as part of that process as well.
Yeah, that's a good one.
Okay, well, thanks, Keith and John. We're just about out of time. Adam has put a link for attendees into the chat where the webinar recording will be available from tomorrow. He's also got his email address there if anyone would like a copy of Keith's slides. Patrick's asked, are they from the ITP April report? I think he's talking about the slides. Is that right, Keith? It's all basically coming from your.
It's all basically coming from the report, yes. But I'll pass the slides on to Adam, and people are welcome to have a look.
That's great. Well, thanks, Keith and John. It's been a really interesting discussion today. Thanks everybody for attending, and we'll see you at our next webinar shortly. Have a good day.
Thanks, everyone.